Good morning, everybody. Today we're going to be looking at Ohm's Law again, but we're going to be drawing circuits and looking at how we can use Ohm's Law along with our little tricks to, there we go, it's clear now, to solve for unknown quantities in circuits. So, on the first four, you're going to actually need the circuit. We're going to draw them, okay? So, let's take a look. First off, you've got your symbols and your notes for what we use, and the first one we're going to make fairly simple. Now, remember, when we draw a circuit, we usually create the circuit loop in the shape of a square or a rectangle because that makes it easier to analyze. So, first we're going to start with the source. Now that's where the electron charges get all their electric potential energy that's then converted in the load. So we'll start with a simple battery. We're going to draw a two-cell battery. So there's one cell and there's the other cell. And the short end is always the negative and the long end is always positive. So one cell is a short line and a long line, and then you just put them side by side. Now this one only has two cells. Now for our purposes, we're going to use the total potential provided. A lot of times you'll see them using a cursive E for EMF, but it's the total potential provided by the source. And in this case, this one has a value of 6 volts. So that'd be like putting two C-cell batteries together. All right, now we need wires to go to our go to the load. So here's one wire from the negative terminal, goes out to the load, and here's a wire from the positive terminal, goes out to the load. Now in our load, we're only going to have one device for right now, and that is a resistor. Now a resistor is used in a circuit to control the amount of current so that it's not too big. In other words, if the resistor was not there and we just connected the two sides of the battery with just a simple wire that basically has zero resistance, the current would become infinite and the conductor would get extremely hot without the resistance to control the current. The more current you have, the more heat you're going to get. So now we have one single resistor. Its job is to convert electric energy into heat energy. So a lot of times that's why resistors get hot. Now, in fact, if you have a good old-fashioned stove with eyes on it, they're basically giant resistors that heat up and heat up enough so that they glow from all the heat. So that's why when you turn on a stove eye, it glows red because it is so hot. Now this particular resistor, notice we use a zigzag line. Now why a zigzag? That's because back in the day, a lot of resistors were simply long coils of wire. And if you look at coils from the side, they look like zigzags, so hence the zigzag symbol for a resistor. Now we need to label. First, we know that which way around the conducting loop is the current going to travel. Well, we know it's actually electric charges, electrons that are moving, negative charges that are moving, even though standard convention is they look at it as if positive charge is moving. I teach it as the electrons moving because we know that's what's actually happening. So the electrons start out with a high potential on the negative side, and they're going to go around as a current flow to the positive side where they have low potential. And the potential difference between the high and the low is 6 volts. Now, when they get to the resistor, potential is used by the resistor. And we're going to call this V1, and it has a resistance R1. Okay? Now, what do we know in this particular circuit? We know that the resistance of the resistor is 2 ohms. And what we want to find is the current in the circuit and the potential used by the resistor. Now, how are we going to do that? Well, normally you'd think, let's use Ohm's law. But if we look, we don't know the potential of the resistor, and we don't know the current going through it. That's two of the three items we need to use in Ohm's law. And when you have a formula with two unknowns, it's not solvable. So there must be something else we can do. And that's where we can fall back on those three tricks that we learned in our notes. There's a trick for potentials, a trick for current, and a trick for resistance. Because we're looking for an unknown potential, we're going to start with that one. We know the rule says that the total potential put out by the source must equal what's used up by the load. Well, there's only one potential in the load, so it has to be the same value as the total. That's just common sense. Okay, so V1 is 6 volts, just like the total potential. All right, now the only other thing we need to find for this one is the current. Now, the current, because there's only one path to follow, is the same all the way around, like water through a pipe, okay? And the potential of 6 volts will push the current charges through that resistance. So, let's use Ohm's law. Now that we know V and R, we can use Ohm's law to find I. IT is going to be exactly the same as the current going through the resistor, so we can say V1 over R1, and that gives us 6 volts over 2 ohms, which, as you can see, gives us a total of 3 amps of current. And we've solved that little puzzle. Kind of cool, right? Now, I'm going to help you draw the second diagram, but you're going to do the solving on your own. Okay? So let's take a look at this next one. We're going to use the same battery as before. Why make life difficult? 2 cells, negative on one side, the short side, positive on the long side, and it provides a total potential of 6 volts. Okay? And we're going to take a wire from each side and to the load, only this time in the load we're going to put a light bulb. Let's use our symbols here today. So there's a light bulb. Now, when the current comes from the negative side around towards the positive, then it has to be pushed by the potential used by the bulb through the resistance of this little filament. Okay, since there's only one device in the load, I use ones for the subscripts on those. All right, so what else do we know here? We know that the current is 0.5 amps, and we know the total potential is 6 volts. We want to find what is the potential used by the bulb and what is the resistance of the bulb. Okay, now notice, because we don't know either of these, we don't have enough information to use Ohm's law, so let's fall back on our tricks. If we want to find the potential, we need to use the potential trick. So V1 is going to be the same as the total, and that's going to be 6 volts. Okay, now we've got V1, we've got I1, because remember all the currents are the same around a single loop, so we can find R1. R1 equals V1 over I1, and I1 is 0.5 amps, so we get 6 volts over 0.5 amps, and as you all know, 6 divided by half is the same thing as 6 times 2, so that's 12 ohms of resistance in the filament of that light bulb. Oh, I was going to let you do it, and I did it myself, didn't I? Oh, well, aren't you lucky? All right. Let's take a look at a slightly more complicated circuit. This is where it gets really fun. Little puzzles. I love puzzles. Okay, we're going to use a larger battery this time. We're going to use 3 cells. How about that? Notice I've been using cells that are 3 volts each. Are they always 3 volts each? No, they're not. That's just a convenient amount. We're going to use a 9-volt battery. Now, you really don't need to worry about how many cells you draw. I'm just picking convenience here. If this were an electronics class where we were actually doing real circuits that are used in, for example, different appliances and in your homes, well, we would worry about the number of cells and how much each one is, but we don't have to worry about that here. Okay, so we're going to come around. All right, in this case, we're going to use two. No, let's not use two. Let's use one resistor and one lamp. Okay, now we have two devices in the load. So when the current comes around from the negative side, okay, it's going to go through this resistor first, so I'm going to call the potential used by that one V1, and it has a resistance R1. All right, and then this bulb would be V2 because it's converting energy just to light, V2 and R2. And if it's incandescent bulb, it'd be a little bit of heat too. All right, so there we go. Now, what do we know about this particular circuit? Well, we know the total potential is 9 volts. We know that R1 has a value of 2 ohms, and V2 has a value of 3 volts. And we want to know what is the total current in the circuit, what is the potential used by the resistor, and what is the resistance of the filament in the light bulb. Okay? All right. Now, notice, we don't know enough information about either of these devices to use Ohm's law yet because we have 2 unknowns for each one. So, we have to go to our tricks again. Well, notice we know the total potential, and we notice the potential used by the light bulb. So we can get the potential used by the resistor because we know whatever the source puts out, the load uses up. Okay? All right, so that means we're going to get V1, we're going to have to say the total, 9 volts, minus what the light bulb is using, which is 3 volts. The only amount left for the resistor to use is 6 volts then. See, that wasn't so tough, was it? All right. 1 down, 2 to go. Here we are. We've got V1 now and R1. Oh, look, we can use Ohm's law right here to get the current in the circuit. So we're going to say the current in the circuit, the total, is the same as what's going through R1, and that would be V1 over R1. So that'd be 6 volts that we just found divided by the 2 ohms of resistance. So IT would have to be 3 amps. Not too bad, is it? All right. And finally, right here, to get R2, all we have to do is realize the current going through R2 is the same as R1. It's 3 amps because it's the same all the way around the circuit. So we're going to say R2 equals V2 over I2. So that would be 3 volts divided by 3 amps, or 1 ohm of resistance in that filament. There we go. And we did it. It's like a little puzzle. Just remember, if you can't use Ohm's law because there's too many unknowns for an item, use a trick. If you can't use the trick, you should be able to use Ohm's law. All right? It has to work one way or the other. Okay. Let's go ahead and draw the last one, and I will leave this one for you to solve yourself using the same kind of strategy that we've been talking about. So in this last one, we're going to go back to a 2-cell, not because it's 6 volts. Actually, in this case, the total potential is going to be unknown. That's going to be one of the things I'm going to have you find. And we're going to draw 2 resistors. just like that. All right, here comes the current. And this is the first device, so I'm going to say V1 and R1, V2 and R2. Now, what do we know? We know that the total current is 2 amps. We know that R1 is 1 ohm. We know that V2 is 2 volts. Okay, now, using that information, you are going to use Ohm's Law along with your little tricks to determine R2, V1, and VT. Okay? All right, I'll leave it to you as an exercise to try to find that. Let's talk about 5 and 6 for a minute. 5 and 6, they want you to draw some simple little circuits with some measuring devices. Ammeter for measuring current, or a voltmeter on number 6 for measuring potential. We're going to draw these, and I'll leave it to you to determine what the value, the unknown value they ask you to find would have to be. But we need to talk about how to diagram with measuring devices. Now remember, the one thing you need to know about measuring devices, ammeters and voltmeters, they just measure. They do not use up energy from the current. They don't use potential. They are not converting energy at all, like other devices in the load. So they are basically invisible to the circuit. Their only job is to measure. Okay, let's start with the diagram for number 6. We're going to draw a schematic or circuit diagram that contains a 20-volt battery, an ammeter, and a 5-ohm resistor in the load. And then you're going to determine what the current reading on the ammeter would have to be. When it asks for a reading on an ammeter, they're asking for the current. Okay? Amps of current, remember? All right, so first we're going to draw a simple diagram here. All right, let's draw the main loop. Here we go. All right, now that's our source and our load. But we also want an ammeter to measure the current. Now, ammeters are ammeters are placed in series with the devices being measured. Now that means, remember, a series is an order, one after another, like the Harry Potter series or the Lord of the Rings series, one after the other. So when the current comes out, we want it to go through our devices, including the ammeter, one after another. So where do we put the ammeter? Well, we could put it right up here. The current goes through it, and then it goes through the resistor, one after the other. It all gets measured, and then it all goes through the resistor. Now that's a series, isn't it? We could also put the ammeter down here and effectively do the same thing. The current would first go through the resistor, then it would go through the ammeter. So that would also be a series, one after the other. So ammeters are always connected in series with the currents being measured. So either way you want to draw it is up to you, either up here or down here. It makes no difference, okay? But we usually do draw an arrow next to the ammeter to show which way the current is traveling through it. So up here we would draw the arrow this way. Down here it would have to go this way because the current's going back to the battery. We have our V1 and R1 for our single device in the load that's actually converting energy. Okay? And now your job is going to be to determine what total current is the ammeter reading. Regardless of where you placed it, all of the current has to go through it to get back to the other side of the battery. So you will be measuring the total current. And they're just simply asking you to determine what value that total current would be, very similar to what we did up in number 1. Okay, so that should be fairly simple. Now let's look at number 6. because on number 6, they want you to draw a voltmeter connected to the resistor. So we have a 2 ohm resistor and we have a battery, and then the voltmeter to measure the potential used by the resistor. So let's draw a battery first. Okay, and then we have a wire coming out and around here. Okay, and the current is coming this way, and V1, R1, since it's the only device in the load, we use a subscript 1 to represent its potential and resistance. Now, we want to draw a voltmeter to measure this potential. How do we draw voltmeters? Voltmeters are always connected in parallel. In other words, we want it to measure V1. Now remember, V1 is a difference in potential between what the electrons have right here when they go in and what they have right here when they come out. They have this, whatever this high potential is right here, that's what they have when they get to this point, because there's nothing here to use it up. Okay? So right here, the potential is the same as it was at the terminal over here. So now we want to measure that. We also want to measure how much potential the electrons have left when they come out, because the resistor is going to use up potential. So we have to have a way to measure on the other side. That's what the voltmeter does. So now we take the voltmeter, draw it side by side, and then we're going to connect it to that point and to that point. So the voltmeter is going to measure the potential here where they go in, it's going to measure the potential here where they come out, and it's going to tell us the difference between those two readings, the difference between the high and the low. Okay? So we call this a parallel connection. So ammeters are measured in series, and voltmeters are measured, or not measured, connected. Sorry guys. Ammeters are connected in series, voltmeters are connected parallel to the devices being used. Okay? It has to be connected to both sides. Alright, I'll leave it to you to determine what potential would have to be measured by that particular voltmeter for that resistor. Okay? Use your little tricks in Ohm's Law to determine what that is. Alright, if you look at the second page of this handout, there's 2 more diagrams you're going to be doing. I'm going to help you with the diagram for number 7, and I'm going to leave it to you as an exercise in puzzling how to determine what they want you to find. So first, we're gonna do part A here. Draw a schematic which contains the following items. It says a 12-volt battery, an ammeter, that's to measure the current in the loop, 2 4-ohm resistors. Now notice, they have the same resistance. And if they're in the series, they'll have the same current. So that means they also use up the same amount of potential. These are identical resistors. That's going to come in handy later. We want a switch and a 6-volt lamp and a voltmeter connected to one of those resistors. All right, so let's start with our battery, okay, our 12-volt battery. 1, 2, 3, and just for the fun of it, 4. 4 3-volt cells. Okay, it did say that we need an ammeter, so I'm going to go ahead and stick the ammeter right there. Might as well measure it as the current comes out. And then it says we've got 2 4-ohm resistors. See, now I'm going to start coming back around, okay? A switch we'll draw it open so we can see it, and a 6-volt lamp. Says we also need a voltmeter connected to one of the resistors. How about this one? All right, so the ammeter is in series with the current going this way. The voltmeter is parallel to the resistor being measured. Now, label, 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 label. Do we label the ammeter with a V and an I? No, we do not. It's not converting energy, but the resistor is. So I'm going to call this V1, and it has a resistance R1. Then the current goes through the second resistor, which is converting energy. Does this have current and potential? No. You don't label that one at all. Just this one. V2, R2. Okay? The voltmeter will measure the V2. The switch, do we need to label it with a V and an R? No, it's just a conductor. It either opens the circuit or it closes the circuit so that current can flow. But the lamp does convert energy. So it's the third device, so we're going to say V3, R3. How about that? Okay? So we have 3 potentials in the load and 1 potential put out by the source. Now, notice it said that's a 12-volt battery. So we know this is 12 volts. Okay? We have 2 4-ohm resistors. That's the resistance. So we know this is 4 ohms and this is 4 ohms. We have a 6-volt lamp voltage. That's the V. So that's 6 volts right there. But we don't know the resistance yet. That's okay. So we know the R's here, and we know the V here, and we know the V there. Okay? Now, we've done the diagram. It's up to you to determine the reading on the voltmeter and the reading on the ammeter. Now, please remember, it said that these 2 resistors are identical. They're going to have the same current going through them because there's only one path for the current to follow, so it has to be the same in both. They both have the same resistance. That means they also have to have the same potential. V1 and V2 would be the same value. Keep that in mind on part B when you're looking for those unknown potentials, because that's going to be part of how you get the potential that's read on the voltmeter for just the one V. Okay? All right, so that should help you right there. And now remember, in part C, you're going to be finding the current in the ammeter. So you might have to find a couple of things before you do that. Remember, it's just a little puzzle, and we're going to use either Ohm's Law or one of the tricks. So I'll leave it to you to see if you can puzzle it out. Okay? Now, I'm going to let you guys draw the schematic for the last one, because it's very similar to this, except instead of having 2 resistors in one lamp, you're going to have 2 identical lamps and 1 resistor. Otherwise, except for the numbers, it's the same circuit. Okay? And you can also, again, then determine the reading on the voltmeter for one of the lamps and the reading on the ammeter. Okay, I hope you guys have kind of some fun with this because they're like cool little puzzles. I like them. I'll talk to you later. Bye-bye.